how can we as chemists change the solubility? How can we as chemists get a solution to form faster or slower? All right, that's what this video addresses. The factors that we can change or just have an understanding of that control solubility. Solubility, remember, is the amount of solute that can be dissolved in a given amount of solvent at a set temperature. So when we say, what can we do to affect solubility? What can we do to change the amount of solute that a given amount of solvent can hold? Where when we talk about what we can do to change the rate of solution formation, this is how fast a solution can form. So solubility is how much solute, and rate is how fast. So let's dig in. The first thing that we need to address is what actually determines if a solute is soluble. What has to do with the chemistry. It is a phrase that we simply just re-quote as like dissolves like. Remember the 3 steps of solution formation, and that third step, the particle attraction between the solute and the solvent. There has to be attraction. They have to be similar in their chemistries, otherwise there's no reason for them to associate. So when we say like dissolves like, we're talking about polarity. So we could substitute in the term polar for like. So polar substances will dissolve other polar substances. We know water molecules are polar. So they're going to dissolve, for example, something like methanol. Methanol is carbon bonded to 3 hydrogens with with an oxygen bonded to a hydrogen. And this side will be our really negative and then our positive. And a water molecule, with the ears being the positive, can come in and form an attraction. Ionic that are soluble. Now, remember, it's an insult to ask if an ionic compound is polar. It is the most extreme of being polar. It's a separation of charge. So, of course, water molecules have the potential to form attraction with ions. Now, why does water and oil not mix to form a solution? Well, oil, fats, the majority are nonpolar, where water is polar. So we can try all we want, but we're going to get separate layers. Now, oil in the liquid state is going to be found on top of the water. Now, that is because of density difference. If it was more dense, then it would be found on the bottom. So it's not because oil lays on top of water. No, the separation is because they have unlike chemistries. But nonpolar can dissolve nonpolar. So for example, if you're working with an oil-based paint, you do not use water to clean your brush or clean your hands. You'll use something like turpentine. And that can remove, the oil-based ingredients or nonpolar ingredients. Okay, so here's just a summary that illustrates like dissolving like. Okay, so how can we get more to dissolve? How can we impact the solubility? Well, first we have to make sure that they have alike chemistries. You can work all day long, and it's going to be incredibly hard to really impact solubility greatly if they are not similar in their chemistries. So here's an opportunity to introduce the terms miscible and immiscible. They are akin to soluble and insoluble. Okay, so you have to make sure that the chemistries are on your side. But the next thing that we can do is change temperature. Remember we looked at solubility curves, and it just so happens that most substances increase their solubility when you increase temperature. But that is only for solid solutes. So what we understand is whenever you increase temperature, you are increasing the kinetic energy of the solvent, and it is able to create and just hold more solute than it would at a lower kinetic energy value. However, with gases, that is opposite. Gases do not want to be restricted in and amongst solvent molecules. So actually their solubility decreases with increased temperature. So we need to remember that. This is showing us ammonia, which is a gas, and sulfur dioxide, which is a gas. So they contradict what we would predict with solids. So far, how do we change solubility? We got to make sure your chemistries are the same, polarities are complementary, and then you can change temperature. If it's a solid solute, usually increasing temperature allows you to dissolve more. For gaseous solutes, though, you want to decrease temperature. The other thing that we can do is change pressure. Now, remember, solids and liquids, they are already touching with no particle separation. So trying to increase pressure, that is not going to change the solubility for a solid in a liquid or a liquid in a liquid. But for gases, Henry's law, the concentration of a gas in a solution is directly proportional to the pressure of that gas over the solution. I have a photo that kind of illustrates this. So, if these purple spheres are gaseous solute, let's say carbon dioxide in the case of soda, and this is the pressure of the gas above. Now, gas molecules, whenever they can, they're going to get out of solution. But if we increase their pressure by decreasing volume or adding more of that carbon dioxide, it's going to actually dissolve more carbon dioxide. That's what we do in soda cans. Now, the pressure of carbon dioxide in the atmosphere, and please do not quote me on this, but it's something like, 0.0001 atmosphere, or crazy low, very, very low. Well, in a soda can, the pressure of carbon dioxide above the solution usually starts at about 2.5 atmospheres. Now, if we increased nitrogen pressure above, it would just help more nitrogen dissolve. If we increase the pressure of oxygen, it would help more oxygen to dissolve. That's actually carbon dioxide. So that's why, of course, when you open the can of soda or the soda can bottle, you hear that escape of pressure, that because the carbon dioxide will effuse out of the opening, that small opening in its container. And then what we see is effervescence. So as soon as that carbon dioxide pressure is released, nothing is encouraging the carbon dioxide to remain in solution, and we see the bubbling. That's called effervescence, the escape of gas that's been dissolved in a liquid. So we can make sure our chemistries are good to increase or decrease more solute. We can change temperature, and we can change pressure with gases, only with gases. Okay, but what can we do to increase the speed at which a solution forms? We can do these three things. We can increase the surface area of the solute. The smaller the solute, the more solvent that can come into contact with the solute. So if we have crushed solute, for example, powdered sugar. So powdered sugar versus granulated sugar, that dissolves much more quickly. We have smaller particles, so more solvent and solute can come into contact. So changing the size of the solute particles, changing the surface area, allows for more solvent-solute contact to accomplish that third step, accomplish that attraction between the solute and the solvent. We can agitate, so stirring, shaking, that brings fresh solvent. So solvent that doesn't already have attraction to solute into contact with the solute. It's all about contact. So that's what this is helping to do, accomplishing that third step of solution formation. This is helping more to come into contact, helping that third step of solution formation? Temperature. Well, temperature helps increase, of course, the kinetic energy of the particles, which puts more into contact, so more frequent collisions and more forceful. More into contact, so helping that third step, and more forceful, so maybe helping with step 1 and step 2 and step 3. So that's just, helping all around. Now, these, except for temperature, do not influence the amount that we can dissolve. You can stir all day long, and if you're at the saturation point, you're not going to get more to dissolve. You can crush the solute until it's just pulverized, but if you're at the saturation point, you can't get more to dissolve. So we're limited. These, except for temperature, don't necessarily get more, but they can help to speed up solution formation. And then, of course, we would do the opposite of these, not agitate or have large solute particles or minimal surface area, or lessen the surface area to get a solution to form slower. So that is a review of the factors that affect solubility and also determine how fast a solution forms.